Welcome to the Homework Solutions video for assignment 3.04 number 2. That's questions 4, 5, and 6 from this section of the textbook. Question 4, a seismograph records the amplitude of vibrations during an earthquake by recording the needle deflections. We got the data for an earthquake 100 kilometers away. And part A, we need to identify the independent and dependent variables. So which are the variables that are happening? So the independent is the one that happens, that generates everything, and then the Richter scale magnitude is the dependent is the response. So if we are looking for this in a logarithmic plot, then that means our independent variable has to be on the x-axis and our dependent variable is on the y. Now in something like this, a test-taking strategy, you can usually answer parts of test questions in any order you want. The test takers or the test makers just see the finished product. So unless you're doing some sort of computerized test that feeds you questions one at a time, in which case there's usually not multi-part, or if there are, the multi-part questions appear simultaneously. In a case like that, you can actually plot the others first. So for example here, we are going to insert a chart after we've entered our data, in this case into a spreadsheet. We see that, yeah, this does look like a logarithmic plot. So it is tapering off close to 0, so that means our independent is the seismograph reading, and our dependent is the Richter scale. So the independent goes on the x, dependent goes on the y. We will customize our series to insert a trend line, and we'll make sure it's logarithmic, and we display the equation. So that's part B, is to create a scatter plot. Part C was determine the equation that models the data. So we have all of that. And then finally D, how many more times intense is a magnitude of 5.7 than a magnitude of 4.5? So that is our intensity. So we're saying when y is 5.7 versus when y is 4.5. So you have to take this graph and find that plot. For that, it's actually going to be easier to use Desmos. So we have a negative 5.66. Well, 5.66, or was it? No, I was right the first time. I said it wrong. 0.566 plus, and then we have 0.472 times the natural log of x. And we need to make sure that our plot is actually going to fit. Our x goes from 0 to 75 million, and our y from 0 to 10 is fine. So we're asked to compare when we have a magnitude of 5.7 to a magnitude of 4.5. That'll be easier if we zoom in a little bit. We see that here we have a 5.827 times 10 to the 5. And here we have a 4.585 times 10 to the 4. So if you take the ratio of those two numbers, 10 to the 5 divided by 4.585 times 10 to the 4. So the difference is roughly 12.7. So it's 12.7 times more intense. So that's question 4. In question 5, so let's slide that up a little bit. The altitude above sea level is a logarithmic function, atmospheric pressure. We need to identify the independent and dependent variables here. So, generally speaking, in a log plot, we're going to have more variation in the independent variable than the dependent. The altitude you head to is what you choose. the pressure is what responds. So altitude should be our independent and pressure should be our dependent variables. We want to find that regression. So for that, we are going to plot the data. And when we insert the chart, we see that this doesn't seem to be working correctly. But again, we need to move our altitude to the x and our pressure to the y. Sorry, no, altitude has to be on the x. So I don't know why. This says altitude versus pressure. The altitude needs to be on the x-axis, and yet this is still putting it on the y. Oh, no, it's just the labels that are messed up. So the numbers are correct here. It's the labels that it's getting incorrect. So if we try for a logarithmic trend, we do get a bit of a logarithmic trend as we are coming down here. So we do have that logarithmic depletion. So for these, the intercepts, all right, well, we have 220 plus that negative, so that 220 seems to be the high point, and that's because this is steadily decreasing. The end behavior, this goes to, in this case, it looks like it's going to go to negative infinity as x goes to positive infinity, and y goes to positive infinity as x goes to 0 from the right. The domain is x a member, or x greater than 0. Range is y a member of the reals, and the function here is decreasing. So if you have a negative coefficient on your log, it'll always be decreasing. If you have a positive coefficient, it'll always be increasing. So the slope is always positive or always negative, and it never flip-flops partway through. So Michael lives at an altitude of 139 meters. Determine the pressure setting that he needs to use to calibrate his watch. Round your answer to the nearest tenth. So here that's a case of y equals 139, find the x. So if we reset all of these, our function is 220 minus 19.8 log x. And here, the range of our x values is going to go to 6,000. And our y values go to about 105. Oh, there we go. Our x had a very negative bend. All right, and Michael lives at an altitude of 139. So when y is 139, x is 59.79. So that's the pressure he needs to work to. And if we have an altitude of 8,848, we need to find the pressure for part D, the atmospheric pressure at the point of Mount Everest. That's at x equals 8848. So it's roughly 40.059 kilopascals. So those are the solutions for parts D and E. And question 6 will finish the assignment. Global warming is causing glaciers to melt in the Mackenzie Mountains along the border between Yukon and the Northwest Territories. And we're going to use carbon-14 dating to figure out the age of an object. So we want to create the scatter plot and find the equation. We want to figure out how old something with 96.8% of its original carbon-14 is, and determine the half-life of carbon-14, the amount of time that it takes to hit 50% carbon-14. So those are our 3 goals. So we're going to start by graphing things. We will insert our chart. And we have age on carbon-14, but This looks like we have our dependent and independence mixed up again. So we are going to fit this to a logarithmic trend line and come up with the equation. So this is the equation that fits our data. We've got the scatter plot. That was part A, scatter plot and the regression function. Part B is going to be graphing this. So our equation is 342 minus 339 ln x, 33.9 times the natural log of x. And our x values here, or the x values are that's the age now. We cannot trust the labels on the graph because those do not automatically switch. So that age is going to go from 0 to 18,000. And the percentage of carbon-14 is going to go from 0 to 100. So we have first a sample that has 96.8% of its original carbon-14 left. So that one is about 1,384 years old. That's part B, and part C is to find the half-life. So that is the value of x when y is 50. So that's about 5,506 years according to this data. So this concludes the solutions to homework 3.04, number 2.